AI is changing everything, right? The way we work, the way we communicate. But here's the catch. This whole revolution needs data. And not just a little bit. We're talking mountains of it. And that hunger for data, it's pushing our computers to their absolute breaking point.
So, what's really going on? The easiest way to think about it is like this. Your computer is a city, and AI, well, it's causing these monster traffic jams on all the data highways inside. So in this explainer, we're going to dig into why these jams are happening, and more importantly, how engineers are basically building new superhighways to fix it all. Okay, so it really all boils down to one word: scale. Just to train one of these big AI models, you have to move these unbelievable amounts of data all around your computer's memory. And this isn't just, a small problem. It's a full-blown hardware crisis.
All right, so here's the heart of the problem. The GPU, the graphics processing unit, that's the powerhouse, the engine that makes all this AI magic happen. But it has its own super fast memory, and there's just not much of it. It's kind of like a genius scientist stuck with a tiny little desk. They can work incredibly fast, but only with whatever papers fit right there in front of them.
And that's what leads us right to the biggest bottleneck of them all. See, to get more data, that GPU has to reach out to the main computer memory, and it uses this connection called the PCIe bus to do it. And that PCIe bus, well, that's our traffic jam. It's like a single-lane country road, and it's causing all the headaches. And when you look at the numbers, you'll see just how bad this traffic jam is. It's pretty wild. The GPU's own memory is just flying, like a bullet train, at 336 gigabytes a second. But that connection to everything else, that PCIe bus, it's crawling along at just 16. 16. That massive speed difference, that's the traffic jam. And it just absolutely kills performance. Now, you might think, okay, can't we just work around it? And yeah, engineers have tried. They have these workarounds that basically force the system to juggle all this data. But it often makes things worse. Trying to constantly shove all that data across that slow connection can lead to a huge 31% hit to performance on average. It's basically like trying to fix a traffic jam by just adding more cars to the road. It just doesn't work.
So if the road's too narrow, what do? Well, here's a clever idea. What if you could just make the cars smaller? And that's the first big solution we're going to look at, compressing the data before it even hits that congested highway.
And it turns out there's this huge hidden opportunity right inside the data itself. So when an AI looks at an image, like the one here, it creates this internal representation. They call it an activation map. And if you look at that map, you see all those black areas? A giant chunk of it is just zeros. It's basically empty space. All that nothing data is just clogging up the pipes for no reason.
Yeah, this thing actually has a technical name. It's called activation sparsity. And get this, researchers found that, on average, a crazy 62% of all the data being shuffled around when you train an AI is just zeros. 62%. So we're not talking about a tiny little optimization here. This is a massive, wide-open door to make things way more efficient.
And the solution they came up with is actually pretty elegant and simple. It's called zero-value compression. So here's how it works. The hardware creates this little map, a mask, that just points out where the real data is, the non-zero stuff. Then it just tosses all the zeros in the trash and sends only the important data plus that tiny little map over the slow connection.
And the results of this simple trick? It's a 32% average boost in performance. Bam! Just by not sending all those useless zeros, this compression trick basically makes that performance hit we talked about just disappear. Think about it. That's like unlocking a third of your AI's power that was just sitting there, stuck in traffic. But okay, making the cars smaller is a great start. But it's only half the solution. Because even with tiny cars, a single-lane road just isn't going to cut it for the future we're building. The whole system is just desperate for more bandwidth. So it's time to build a brand new express lane. And that express lane has a name, Compute Express Link, or CXL for short. If you look at this diagram, you can see how it works. It uses that fast PCIe connection we've been talking about, but it uses it to plug in a whole new layer of memory. It's like adding a dedicated on-ramp for more memory right next to the processor. So how does this new CXL memory compare to what we already have? Well, the regular system memory, the DRAM, is still the absolute fastest, but you can't have a lot of it. It's super limited. CXL comes in and adds a ton of extra capacity that you can scale up, and it's still really fast. So the total amount of bandwidth the whole system can use just goes way, way up. And the numbers in the real world? They're seriously impressive. Some research from folks at Micron and Intel showed that just by adding the CXL Express lane, you get a 24% bandwidth boost for tasks that do a lot of reading. And for those mixed workloads, reading and writing at the same time, which is super common for AI, that performance jump can be as high as 39%.
Okay, but you know how it is in engineering. There's never a free lunch. All this new super fast tech, like the PCIe 5.0 that makes CXL possible, it comes with a pretty serious side effect: heat. A lot of heat. It's a simple equation. More speed needs more power, and more power makes more heat.
And you can really see the jump in this table. So a fast storage drive on the older PCIe 4.0 standard, it might sip around 7 watts of power. But these new PCIe 5.0 drives, the ones we need for CXL, they can pull down up to 15 watts. That's more than double the power, and pretty much all of that power turns directly into heat. And that heat has a direct and, honestly, kind of a shocking impact on performance. When you're really pushing it, one of these new drives can actually overheat in just 5 minutes. And when that happens, it has to protect itself. It does something called thermal throttling, which means it slows itself down by over 30% just to keep from getting damaged. So it literally erases the very speed gains you bought it for in the first place.
So that brings us to the last piece of this puzzle. We've got to deal with the heat. Right now, engineers are coming at this from 2 main angles. You've got active cooling, that means fans. They work great, but they can be loud and bulky. Then you have passive cooling, which is basically big metal heat sinks. They're silent, but they really depend on good airflow in the whole computer case. And as you can see, each one has its own set of pros and cons.
All right, let's zoom out for a second and look at the big picture here. This whole story we just went through, finding a problem, coming up with a smart fix, and then having to solve the new problem that fix created, that's basically the story of computing. It's this constant cycle of innovation. And you better believe the industry is already thinking about what's next. We're going to see PCIe 5.0 become pretty standard by 2025. Then by 2026, we're expecting to see new stuff like gallium nitride chips that will make everything way more power efficient, which means less heat to deal with. And after that, PCIe 6.0 is on the horizon, and the big goal there is to double the speed again, but this time without doubling the power. That would be a huge win. So all of this leaves us with one really big question for the future. AI's appetite for data is just exploding. It's growing exponentially. But our hardware improvements, they tend to happen one step at a time, more linearly. So can all these clever engineering tricks keep up? Or are we heading for a future where AI's hunger for data just completely outruns our ability to build machines that can actually feed it?